Thank you, Pierre-Louis. Thanks a lot for being again here, which is a big honor and even bigger pleasure. Last time we were here to celebrate the 85th anniversary of Claude in 12th of April, where I was talking about quantum Claude. And it's my favorite pastime when I'm in Paris. I always try to be here on Friday because in the morning I can go to the Séminaire of Pierre-Louis Lions, and in the afternoon there's a Séminaire at the Laboratoire Jakob Lions, where Nicolas Vissilia will talk today about something more technical. He will go into more technical details than I will do in my talk. So it's so we have enough time for lunch and then move over to Jakob Lions. So you see a lot of Pauli in my title. So not everybody not everybody, but in our community, everybody knows Dirac equation, everybody knows Schrödinger equation. In between, I will explain what I mean by in between, there is the Pauli equation that I'm working on for a long time. And it fits well that I'm director of the Wolfgang Pauli Institute in Vienna, which carries also in Institut CNRS Pauli. And I'm also a professor at the University of Vienna, where I'm head of a platform between mathematics, physics, and computer science, which deals with magnetism. So when you hear Pauli equation, magnetism is there. So I could spend now 2 semesters on explaining all the equations here. So the purpose of this talk is to really explain the model. What is a self-consistent Pauli equation? As you see, I say self-consistent Pauli equation. Each of the boxes here is at least 50 publications of top-notch PDE analysts. We talk about nonlinear systems of PDE. So what is this modeling? So we have one PDE for what I call the particle. If I talk about Dirac-Maxwell, I talk about fermions, so typically an electron. Which is modeled by psi in physical space, which is a spinor, and I will explain this. Then from this equation, you get some charge density or current density. That I will denote by rho or J. In relativistic quantum physics, these are the 4 components of the 4 vector. And then we have an equation for the electromagnetic field. Or potential. So if you know Maxwell equation, usually they're formed in terms of the field, but you go from the field to the potential by the Coulomb potential. So you say the electric field is minus for some convention the gradient of a potential, and the magnetic field is the rotation of some. So this is meant when we have these models. So for example, we have the Dirac equation coupled to the Maxwell equation for this electromagnetic field. And if you do speed of light to infinity, so this Dirac-Maxwell is a fully relativistic system. So by special relativity, speed of light is not infinite. You have no instantaneous interaction. And you have the Maxwell equation that was known a long time before quantum mechanics was invented. Then Schrödinger invented the Schrödinger equation about 100 years ago. And then Paul Adrian Dirac had a well, he's a genius. So people were looking how to generalize the non-relativistic Schrödinger equation of Newtonian physics coupled to the Poisson equation, which is instantaneous interaction. So all the universe knows immediately what happens at the rest of the universe. If you say speed of light is bounded, so if I move an electric charge here and I observe here, it takes speed of light some time until it reaches this distance. So magnetism intrinsically is a relativistic effect. There would be no magnetism if speed of light would be unbounded. It's very important to note. Okay? So then Dirac was thinking, how can we generalize Schrödinger equation to something that is relativistic? And it's a very interesting story. He found out it cannot be a scalar, it has to be a vector. And out of some Clifford algebra considerations, he found out these 4 components. So psi for the Dirac equation is a 4-spinor. So you have spin up, spin down, spin up, spin down. You have an electron component and a positron component. And this is a really fascinating story. He was generalizing it. He came up with an equation. If you take the free Dirac operator without electromagnetic field, just of the free particle, you see that the spectrum has also a negative part. And Dirac, I mean, at this time, everybody was physicist and mathematician at the same time. Dirac, he has the culot, he has the guts to say, well, this is negative energy, so there is antimatter, there is particles with negative energy. So just out of theoretical considerations, he postulated there is particle-antiparticle because in my operator I have negative energy. And we know now perfectly there's the positron, which is the antiparticle of the electron, and that's why you have 4 components. So Dirac equation, I will also denote the Schrödinger equation, is a relativistic version of the Schrödinger equation that lives on a 4-spinor. Now if you're on the level of Schrödinger, or even, I will introduce also magnetic Schrödinger. Psi is a complex, so that's very important, is a scalar. So you have a 4-spinor for Dirac equation, you have a scalar for the Schrödinger equation. In between, if you take, I will explain it, the Pauli equation, you have a 2-spinor, spin up, spin down. Whatever you imagine, it's a quantum number that's related spin up, spin down to the famous Pauli exclusion principle. So 2 quantum particles must not be in the exactly same quantum state. So if all quantum numbers are the same, you can distinguish 2 different states. And that's the explanation of the periodic table of elements. Okay, so this is a major progress in science that Pauli came up with this exclusion principle. It's just a manifestation that the many-body wave function has to be antisymmetric, but it comes down to the so-called Pauli exclusion principle. So what we have here in this, we have the black boxes, which is more or less standard knowledge. So if you take the Dirac equation for the 4-spinor, you can now make a self-consistent model. So if a charge moves very fast, close to speed of light, you need a relativistic model. And then the moving charge will create an electromagnetic field interacting with the particle itself. So a moving charge creates its own magnetic field. That's what we call self-consistent. Of course, you can also be in the laboratory with strong magnets. You have a tokamak, you have a collider, or whatever situation where you have a very strong external field that does not depend on the moving charge and on the density. Then you have both a nonlinear part, which comes from the self-consistent coupling, and a linear part. Okay? So on the level of Dirac, and there's also, I just mentioned it today, Dirac equation is for fermions, so for particles with spin 1/2, so we have spin up, spin down. Klein-Gordon-Maxwell would be a model for bosons. It's a scalar equation. It's mathematically distinct. It has some similarity, in some sense, the square of the Dirac equation, but this is very vague. I will not talk about bosons today. So today I will only talk about electrons. So, and Dirac-Maxwell is my starting point. We are on the level of one particle equation, which can be an effective model. Indeed, you would have the n-particle problem, and you do some limit weak coupling. I will leave that out today. That's what I presented when I was talking about my work with Claude Bardos, where we did this kind of derivation of non-linear one-particle model from linear n-particle model. The reason is simple. You can derive Schrödinger-Poisson from the linear many-body Schrödinger equation by this kind of weak coupling limit. That's rigorous work. But the starting point is the non-relativistic many-body Schrödinger operator, which is well settled. I mean, you have two particle interaction by Coulomb interaction or contact interaction if you want to derive Gross-Pitayevsky. On the level of relativistic quantum physics, there is no many-body quantum relativistic Hamiltonian. All the attempts of doing with retarded potentials, Breit-Wigner, is not really satisfying. So there is no derivation at all from the many-body picture towards Dirac-Maxwell. So this is my starting point. And Dirac-Maxwell has electrons and positrons. So you can convert energy from the electromagnetic field into a pair of electron and positron. You can create an annihilate. That would be the starting point of doing quantum field theory, where you create particles and you're in Fock space, where you have all the implications of going with a varying number of particles. So Dirac-Maxwell is considered as the exact model. This is a nice model. I mean, mathematically, there is still open problems in 3 dimensions. Global and local well-postness is still not completely settled. The model is consistent. Both are relativistic equations, so both are Lorentz with Tz, I will come to that point. Lorentz invariant, so you have Lorentz covariance. So this is a fully consistent model. Both equations, Maxwell and Dirac, are both fully relativistic and it fits together. Just one remark. When you go from the field to the potential, you integrate in some sense. So you have 1 degree of Friedrom, and this will enter as a gauge. So that's a choice you can do. So independent of the gauge will change the form of the equation for the potential, but the gauge will not change. It's a fully relativistic model. Now, when you do the non-relativistic limit, you make a small parameter, 1 over c, and you let c go to infinity. You end up with a Newtonian physics. There is no magnetic field, there is no spin, and you can couple to what is left over of the Maxwell equation, which is Poisson equation. If you ever write down Maxwell equation and you put the 1 over c in the equation, and you say that's 0, you inherit terms, and everything that is left over from Maxwell equation is Poisson equation. So Schrödinger-Poisson is the limit equation, but now there is a model hierarchy, and in the middle there is this Pauli equation that I will explain. So Pauli equation is at first order in 1 over speed of light. So you really have an approximation. So you improve Schrödinger equation by going, which is first, so there is one of the parameter with power 0. So this is order 1. This is of all orders, and here you're in the first order. And so you have the Pauli equation, which is an approximation of the Dirac equation or a correction of the Schrödinger equation. Okay, so the red boxes here, these are models that are studied for decades by top-notch PD analysts. In particular, there is the magnetic Schrödinger coupled to Maxwell. But there's a problem. All these red models are of order 1. So they are of the same precision as Schrödinger-Poisson. Okay, because if you have, so that would be Laplace. That essentially, let's add maybe the h bar square over 2. So that's the Schrödinger equation. Now if you make this operator is the magnetic Schrödinger operator. Okay, so you have the scale 1 over c. So if c goes to infinity, this disappears. You, instead of gradient square, Laplace, you can, divergence of gradient, you can write this gradient square. You have this magnetic Schrödinger operator. But if you do the Pauli equation, you have a term which I denote as sigma. So these are the Pauli matrices. I will note it down. Sigma, this is corresponding to spin. It fits because the Greek letter sigma corresponds to the first letter of spin. And this is magnetic field. So you have a coupling of spin and magnetic field. So these are two matrices. I will write them down, the Pauli matrices. So you have this extra term that goes with 1 over c. So this is a first order term. This is called the Stern-Gerlach term. I will present it in one of the transparencies. So if you start with Schrödinger equation, which is fully non-relativistic, and you go to magnetic Schrödinger, you introduce the magnetic potential. So this is first order in 1 over c, and there's even a second order term. But if you do not include the Stern-Gerlach term, this spin magnetic field coupling term, you still miss a term of order 1, of first order. So magnetic Schrödinger-Maxwell is a system that was treated a lot by mathematicians, which has one big disadvantage from the modeling. It's still at the same order of precision than Schrödinger-Poisson. You introduce magnetic field, but you do not gain in the nonlinear coupled system an order of, you do not improve for 1 order. Of course, if you think of the spectral problem of Laplace, and you go now, here you add any potential, you enter a world of pain. So going from Schrödinger operator to magnetic Schrödinger operator is already mathematically a big challenge. Okay, so this is, and now we do it in a self-consistent way, so this A will be the solution of Maxwell equation. Okay, so this is one model where is a lot of interesting work. Then you can, if you couple to Maxwell or you couple to Poisson, it's the same precision of the system. You skip a first order term, so if you do Maxwell or Poisson, so Maxwell equation is fully relativistic in all orders of the small parameter 1 over c. So if you couple to Maxwell or to Poisson, the overall system is order 1. And you can also take Pauli equation, so I will explain what Poisswell mean. You can couple Pauli to Poisson. So these red boxes, everything is on the same order of precision as Schrödinger-Poisson. Only the Pauli equation coupled to some equation between Maxwell and Poisson. And when Nader Masmoudi and I were working on this about 25 years ago at Courant Institute, we coined the name Poisswell. It's known, especially in plasma physics, as the magnetostatic approximation of the Maxwell equation. So that's, in the quantum context, was completely new. And there is also the Darwin term if you go then to second order in the field term. So these are the quantum models. And this error here has been done. So we are able to pass from Dirac-Maxwell for the non-system to Schrödinger-Poisson with Pauli-Poisswell in between. Then you have a second line of h bar to 0, classical limit or semi-classical limit. So there you pass from quantum mechanics to classical mechanics. So if you take relativistic Vlasov equation, what do I mean by relativistic? So the velocity, which is unbounded, becomes a velocity depending on psi with the gamma factor. So you get psi This is the famous gamma factor that you know from special relativity. So if c goes to infinity, you get the unbounded velocity. So this is bounded by speed of light. So whenever you say relativistic Vlasov, you have to modify the Vlasov equation in a way that instead of having the unbounded velocity, you take a bounded velocity by this factor. So this is meant by this REL dot. So and then there's the Lorentz force, because of course the magnetic field enters also in the force term. So that's a fully relativistic classical system, no quantum mechanics. And if you do the limit of speed of light to infinity, you end up with Vlasov-Poisson. And if it's monokinetic, if you take a pure state, you end up with Euler-Poisson. The same here. So there is a lot of work on Euler coupled to Maxwell, Euler coupled to Poisson, relativistic Euler coupled to Maxwell. So there is many top-notch PD analysts who have worked on that. In between, you have Euler coupled to a new system which is purely elliptic, the Euler-Poiswell or Euler-Darwin system. Okay? So this is the box. There would be a third asymptotics that I will not talk about today. So the rest of the talk, I want to explain you some terms and some tools in this context. Okay, so again, for each of the box, you have many, many publications. This error, h bar to 0 here, is not done yet. We are currently working on Dirac with a time-dependent potential towards relativistic Vlasov with François, Chiara Safirio, and Nikolai and Jakob. So I have to just to say one thing, what I present today is mainly work with Jakob Möller, who is here today. Part of the work is together with Changhe Yang, who is a PhD student of Tom Hu at Caltech, Pierre Germain, and concerning this limit for the Dirac to Vlasov, relativistic, and for the averaging lemma, it's François Golse. Good. So what I want to explain is what is this Pauli equation. So I put two superscripts to denote that I have two parameters I can play around. So each, in the Schrödinger equation, each derivative comes with an h bar. So you have something oscillating on a wavelength of the Planck constant. So h bar is the Planck constant. So here I have the time derivative. So here is what I already wrote down, the magnetic Schrödinger operator, the Coulomb potential term, and here we have this coupling of sigma to the magnetic field that comes with the factor 1/2. Actually, this is the Pauli equation, and it was immediately successful. So Pauli reduced the full Dirac equation. He said we don't need negative energy positrons. So Pauli introduced the Pauli equation, and there was some fine structure in the spectra. This was a very important problem at the time. Physicists were observing spectra, and they were looking for a theoretical explanation. And then it turned out that you need precisely this factor 1/2 here, and Pauli equation could explain some fine structure in the spectra. This was a major triumph of what we could call mathematical physics. So this is the Pauli equation, which is Schrödinger equation with the magnetic Schrödinger operator plus this extra term. Then for the potential here, like in Schrödinger equation, you have the Coulomb. So I talk only about 3D. In 3 dimensions, the Green's function of Laplace is 1 over x, 1 over the distance, which coincides with the Green's function of Laplace. So you would have the Hartree equation. So if you derive the equation, you get 1 over x convoluted with the density, and then you rewrite this integral form as Poisson equation in 2D and 1D. That's no longer the case. So magnetic fields in 2D and 1D is a very strange business. So everything I talk about today is 3 dimension, which is the correct setting for magnetic fields. And then what you see here is what I call the Poisswell equation. So this is Laplace of the vector potential equals 1 over c, the current. So this is the current that now, in the context of the Pauli equation, so imaginary part of psi bar gradient psi, this comes from this is for the Schrödinger equation. Now, of course, you make this gauge invariant. You introduce here already for the current, you introduce this potential, and then you have a divergence-free term here where the spin enters in this extra term. So the definition of the current for the Pauli equation is quite involved. Okay, so you take, this is again what I said here, you have one equation for the particle, which is now Pauli. You define the charge and the current, and then you plug it in as the source term into what is left over. In the Maxwell equation, you would have 1 over c squared second time derivative for the hyperbolic system. So you cancel the second order terms, and you end up with something in first order. Okay? So that's something that is really in between Poisson equation, but you add 3 equations for the magnetic potential that are elliptic. Why do we do that? Why don't we simply couple Pauli to Maxwell? This would be first order. Well, Maxwell is hyperbolic. If you think in terms of analysis and numerics, you would prefer a priori elliptic equations to hyperbolic equations. And indeed, people in plasma physics, they call this approximation the magnetostatic approximation, Maxwell equations. They use it quite frequently. So this magnetostatic approximation is used when you couple Vlasov to this kind of Poisson equation. Now, as I said, you have the choice of the gauge. You integrate once from the field to the potential, and there is 2 choices that are natural, and that's for your convenience. And if you do Lorentz gauge, careful, that's Lorentz without a T. So there is Ludwig Lorentz, who introduced the Lorentz gauge, and there is Hendrik Lorentz with TZ, which is more known, who introduced the Lorentz covariance and the Lorentz transformation. Okay, this is, many authors in their papers mixed it up, but this is 2 different people, although it's both in relativistic quantum physics. Okay, so you see, you take away this 1 over c term here. This is just divergence of A equals 0, which is called Coulomb gauge, and that's a choice. You are still in a fully consistent relativistic model at order 1 over c, but this is a choice you can do that does not have an impact on the physics. So if you do here, you take the Leray projection on divergence-free fields, you get something that is order 1 over c squared, that is called the Darwin term. So when people study approximations of Maxwell equations, it's well known, there is a Darwin term, okay, that occurs here, which is the Darwin approximation of the Maxwell equations. On the quantum level, we shall see there is also a Darwin term. The same name appears twice. So you can make a second order correction to Schrödinger equation, which is called the Darwin term, and you make a second order approximation to Poisson equation, direction of Maxwell equation, which is called the Darwin approximation. So we have Lorentz and Lorentz with TZ, and the word Darwin appears in two different contexts. Once for the particle description, a second order term, once a second order approximation here. And this sigma here, so you have a 2 vector, and one of the Pauli matrices mixes the two components. It is not all of 3 of them diagonal. So that's the Pauli equation, self-consistently coupled to electromagnetic fields with this special definition of the current. Just to mention, if you go to 1 order more, you have terms. There is the Darwin term, which is second order in 1 over c squared. You have a 4th order derivative. You can also cook up a model that we were given with the subscript 2. This would be a second order model, but we don't look at this. There's no analysis for that for good reason. Okay, so this would be a consistent second order model. Okay, and as I said, you get 1 plus 3 Poisson equations, and we call this magnetostatic approximation. Okay, and from the 2 parameters, you can play with 1 over c going to 0 and h bar going to 0. And again, if you do relativistic quantum physics, you gain magnetism or spin. So the Pauli equation is the first equation where both relativistic effects are in, so that's it's close to Schrödinger equation. Dirac equation is a different story. It's a first order PDE which has different properties. So in some sense, you correct Schrödinger equation with first order terms and you gain Pauli equation. Okay, so as I said, we are in 3 dimensions, and so just a glimpse on the analysis. If you couple Pauli equation both to Poisswell and Darwin, this is a recent work that we just finished with Pierre Germain and Jakob. Well, it's not very satisfying, so we gauged local well-posedness in a solver space with 3 half derivatives, and we only get non-unique global weak solutions. That's what you get if you work hard with a top-notch PD analyst like Pierre Germain. Probably if you use Bourgain spaces and go deep into this very advanced method, you can do better, but that's a technique that we didn't want to use. And the main estimate, the main difficulty is to get good estimates for the time derivative of this magnetic potential. So that's one of the work that has been done. Now, of all these quantum models, Dirac-Maxwell, Pauli-Poisswell, if you do if you do C to infinity, you end up with Schrödinger-Poisson. And so Schrödinger-Poisson is a well-studied system. There is still a lot of work done on Schrödinger-Poisson. It's a model that is used in several applications. And the non-empirical limit is you need the bilinear estimates, these null forms of Kleinerman-Macedon. So there was myself with Béchouche and Sigmund Sellberg, and then Masmoudir. So Sellberg was a PhD student of Sergio Kleinerman. Kenji Nakanishi was a postdoc, and it was clear that in order to get the uniform estimates in 1 over c, you need this quite involved technique. And even a technical monster like Nadia Masmoudi, he decided not to do it alone, but hire a postdoc of Sergio Kleinerman to turn this machinery of these bilinear estimates. On the level of h bar to 0, you end up with Vlasov-Poisson, so Poisson equation coupled to Vlasov equation. There could be both signs here. So this is a well-studied equation, Vlasov coupled to Poisson. So this is the simple low collisions, and you couple the Poisson equation. And Vlasov-Poisson, for the gravitating case, is heavily used by people in cosmology. If you ever see these pictures of the universe where they say the galaxies are distributed in a non-uniform way, there's this beautiful, and the telescopes now make this observation. So they can reproduce what we observe in the sky, the non-uniform distribution of galaxies. You get a very good description. They start to murmur about Einstein equation. At the end of the day, these people solve Vlasov-Poisson with very advanced techniques. Okay, so Vlasov-Poisson is a very useful model, and you can derive a limit from Schrödinger-Poisson, and this was by Pierre-Louis and Thierry Paul and Peter Markowich and myself in the 92, 93, where we found the trick how to do that. I will shortly present that. And then if you take a pure state, if you have monokinetic phase-space distribution, you end up with Euler-Poisson. And again, here for Euler-Poisson, the two cases, attractive or repulsive, are very different in the mathematical setting. It's amazing that for Vlasov-Poisson, for both signs, you use the same proof, but for Euler-Poisson, it's a different story. There is one I just mentioned. If you say my magnetic field is very strong, they're very strongly confined in the tokamak, I don't care about the self-consistent potential. This is somewhat cheating, but not really. You get, of course, only coupling to Poisson equation, which mathematically is much easier. Okay? So this has been done by Jakob in his thesis in a paper. Now the semi-classical limit, if you want to converge the horizontal error from Pauli coupled to Poisswell or Darwin to Vlasov type equations, if you want results for all times, because Euler equation limits also, they are only local. As soon as the Euler equation has a shock or something, you are done, you are local in times, but with Wigner measures, with the Wigner method, you can do it global in time. So you get some weak convergence. So I briefly sketched the idea. If you want to do semi-classical limits, there is very little results on what is called the pure state, where you have only one Schrödinger equation. What you use are infinitely many Schrödinger equations. So the index J here goes from 1 to infinity, and you have occupation probabilities. So you cook up an object, so the density matrix, which is the kernel of the density operator, is an operator in L2. So with this object, so quantum statistical mechanics is on the level of density operators. Okay, so you have infinitely many coupled Schrödinger equations. They are coupled by the definition of the density and of the current, and then you plug it in our 1 plus 3 elliptic equations. So that's the starting point. It's the Wigner function that you construct. So you take the density matrix, center of mass and relative coordinates, you make a Fourier transform with respect to the relative coordinates, so you end up in phase space. This is real valued, but it can oscillate with negative values. However, if you smooth it with Gaussians, where the variance is at the order of h bar, you get what is called the Hushimi function, you get a non-negative function, and in the limit, the accumulation points coincide. You pass to a positive measure, which is called the Wigner measure, in the paper of Pierre-Louis and Thierry Paul. And in their paper, they use what is called coherent states, and we use Hushimi functions, which is equivalent. So there is a well-developed technique of h bar to 0, quantum to classical, for global in time results using Wigner transforms. Okay, so you end up, this is the Lorentz force, velocity or momentum with the magnetic field, and you end up with this model. Now, if you use mixed states, it complicates things. You go from one space variable to two space variables or to phase space. So this is, of course, in some sense, for numerics bad news. What you gain is the possibility to make these occupation probabilities depending on the Planck constant. And that's exactly what you need. If you want a uniform bound in L2 on the Wigner function, you only can do it if the sum of the square of all the occupation probability, 1 over h cubed, is bounded. So if you want to do a semi-classical limit, you have to use mixed states, and even worse, you have to use mixed states where the pure states or finite number of states are excluded. You need exactly this sum over all occupation probabilities is bounded by h bar to the cube. So that's very convenient for mathematicians. You want to get a uniform bound. Okay, you change the physical model. You go from one Schrödinger equation to infinitely many, or to the equation for the density matrix, and what you gain is a uniform bound. You can do it in one space dimension also for pure states, but that's a different story. Okay, so you can pass to the limit from the Pauli equation with all these terms coupled to elliptic equations for the electric-magnetic potential. You can pass to the limit using Wigner transforms. If you do it for the full Poisswell system, we do not have enough regularity yet. I will comment on that. If you couple only to Poisson equation, that was done, that you can do, and what you'd use are magnetic leap theory estimates. So for the Pauli-Poisswell, the convergence to relativistic Vlasov-Poiswell is a conjecture. So the Vlasov-Darwin system was studied by Christophe Ballard, a PhD student of François, and also later by Seehaber. And the key problem we have is a lack of compactness. So there was a very vague idea. When I was young, people were talking about averaging lemma, the lemme de moyenne, that Rémi is here today, that Benoit could not come, that François Golse, Rémi Sentis, and Benoit Patam introduced, and then with Pierre-Louis made a complete paper on a tool how to gain regularity by velocity averaging. So my hope was, if we can do a quantum averaging lemma, a semi-classical averaging lemma, maybe we gain the regularity that we do not get. In fact, when I was cooking up the Pauli-Poisswell model with Nader Masmoudi 25 years ago, we tried to do the limit, and always a little bit of regularity was missing. So we were working for 2 weeks, and we did not succeed. And then we said, well, maybe we wait until some new tool is found. Now, François and Jakob, they were developing, and we wrote the paper, the three of us, introducing the tool of this averaging lemma that is in classical sense. So you have the transport operator, and then everything that comes from Boltzmann equation or Vlasov equation, you denote it as S of f. So this is some sort of generic term. Now, if you integrate in velocity, you go back to physical space, you start with L2 and you gain some regularity. So that's what is meant by velocity averaging, which was a very important tool for several Vlasov-Maxwell, and there were several of these nonlinear PDE systems. This is a tool, and several authors up to the last years have developed this original idea. I should say Agoshkov also at the same time had a similar idea. So this is something that is known in the kinetic community as averaging lemmas, and I call them classical. Okay, so for example, Rondi, Perna, and Pierre-Louis used it for Vlasov-Maxwell. Now what we did was we said, okay, the Wigner equation in the kinetic energy has the free transport operator. Then here this is a pseudo-differential operator in the potential. So it has the form like for the averaging lemma. Can we adapt it? Yes. We can do quantum averaging lemma. This is just a little remark. And of course what we need is something semi-classical, uniform in h bar. And what you gain is 1/4 of a derivative for the linear case. We are not yet there for the nonlinear case, but at least, so with François and Jakob, we could introduce quantum and semi-classical averaging lemma as a tool that maybe one day might be useful for passing to the limit for Pauli-Poisswell. Okay, I'm perfectly in time. So just to finish up, so when we do the semi-classical limit to Euler-type equations, so if you do semi-classical limits, you have the choice of Wigner transforms, that is global in time, weak limits with this tool in phase space that I introduced. You can also do a more classical approach. This is Wenzel-Kramers-Briand, the WKB method, which is based on a particular ansatz. You take one Pauli equation, you take one Schrödinger equation, and you make this ansatz with an amplitude and a phase, and then you make this ansatz. This corresponds to a pure state, and pure state corresponds to monokinetic phase space function, so you end up with Euler equation. Okay, so you start with Pauli equation coupled to this Poisswell equations, and this I mean by monokinetic. So your phase space, P now is the velocity, the momentum, so you end up with a delta in velocity that's monokinetic, and here you have the density. And this works for short times. So the WKB ansatz breaks down as soon as the underlying Euler equation, the hydrodynamic equation, develops the first shock. So this is clear. WKB methods are somewhat, not simpler, but a different approach, which from the beginning is only local in time. Okay, so I skipped the details, so you have to convert your Pauli equation into a Pauli equation for this ansatz. So you get Euler-Poiswell, where you have here the Poiswell equation, and you get this form. This is an Euler equation coupled to the Poiswell equation. So this is with some initial data here. Okay, so this is a result that we did with Changhe Yang, and working on the limit from Pauli-Poisswell to Euler-Poiswell and Euler-Darwin, we were faced with the problem of the existent uniqueness theory of Euler-Poiswell. Euler-Maxwell, relativistic versions of Euler equation, where you still have some sort of gamma factor entering. So relativistic Euler-Maxwell is a quite hard problem. There is some results in top, I think it's even in Jonas' paper. So this is very, very hard PD analysis. Euler-Poisson is also hard, depending on the sign, attractive or repulsive. So for the Euler-Poiswell, this was mainly the work of Changhe Yang, who comes from Peking University, and then, I mean, this is like people from École Normale or École Polytechnique. You say, okay, take the paper of Maider and try to adopt it to our situation. Then 3 months later, they come up with a. So these are Peking University, Tsinghua University are technically on the level, I would say, of the Grand École in France. So he came up with a blow-up alternative for this Euler-Poiswell system, which is a new system that we cooked up here. Okay. And then you can also do that in second order, which is the Euler-Darwin equations. So again, Darwin means that between Maxwell equation and Poisson equation, you make a second order approximation in 1 over speed of light. That's the word Darwin. So there's Vlasov-Darwin, there's Euler-Darwin, and this is Jakob introduced in his PhD, and we were working on that. Okay, so for Pauli-Poisswell to Euler-Darwin, we have a theorem. Okay, I don't enter the technicalities of this proof. So if we take these two approaches, the h bar to 0 limit, so I go back again to my first of all this. Okay, so you couple the Pauli equation, again, magnetic Schrödinger plus a first order 1 over c coupling of the Stern-Gerlach term of spin magnetic field. So on this level, you can do this limit either with Wigner, globally in time, or with WKB, locally in time. Intermediate result, the Pauli coupled to Poisson, this is fully done. So this limit was known. This limit for the fully nonlinear system is still open. For the linear problem with time-dependent magnetic potential, we get some preliminary results, but full Dirac-Maxwell to full relativistic Vlasov with Lorentz force Maxwell is out of reach. On this level, you have the problem that in the Vlasov equation, you have a gradient of the potential. In quantum physics, the potential enters as a multiplication. In classical physics, you have the gradient of the potential. You have to control a full derivative more. So in some sense, the classical situation mathematically sometimes is harder than the quantum situation. So on this level, there is some results, but nothing really satisfying. Here, there is satisfying results, and here that's new results, both existent uniqueness of Pauli-Poisswell, Pauli-Darwin, which is order 1 over c, and the limit to this quantum model. Okay, so that's what we have for the moment. A new tool has been we are starting, so especially François and Jakob, the quantum and semi-classical averaging lemma, maybe the tool that will bring the missing regularity. And again, since 25 years, we are stuck at the point where a little bit of derivative is missing to pass to the limit. I don't think it's a problem of the physics, it's a problem of the mathematics. Okay, and so both methods for semi-classical limits are exploited on this level. Last outlook, so on the level of numerics, of course, you have the advection operator if you take Pauli equation. So if you square this term and you keep also the So you have this advection term. So this is for the linear Pauli equation. We have good numerics. So now we're trying to adopt what Lubich was doing for Schrödinger-Poisson to Pauli-Poisswell. Again, we have this coupling of the two components here. This is highly non-trivial. Okay, so numerical proofs for nonlinear equations to give proofs of this sort of operator splitting. This is something we might work out with Shi Jin at the Chinese school. This is something on our program. So to sum up, so these are the works that I was reporting. So this is mainly the work of François with Jakob, but we wrote now a note class that was just submitted where we really explain what we are doing here, classical quantum and semi-classical averaging lemma. And so there is the work with Pierre Germain on the local and global well-postedness of Pauli, Darwin, Poisswell. And this is the paper on the semi-classical limit. And there is still, so the model, Pauli equation coupled to Poisswell equation is the good model. It's the only model that is consistent between Dirac-Maxwell and Schrödinger-Poisson. All the other models are mathematically interesting. Schrödinger coupled to Maxwell. You miss the first order term in the Schrödinger equation that has to be there if you really do a consistent first order in the small parameter approximation. So this is a new model, and in between there is Euler coupled to this kind of elliptic equations, which is a nice mathematical work. So that's the state of the art on a consistent first order relativistic improvement of the Schrödinger equation, including magnetic field and spin. Thank you.
Thank you.